So we can see that the isokinetic dynamometry, and I've isolated, I've shown some examples there, limited examples, is relatively reliable, particularly under kind of averaging. It's more reliable generally under concentric than eccentric, but that is really about ensuring that we've kind of got a familiarization incorporated in. And one of the things to recognize is that, yes, you can do, your 5 trials, discard the first, discard the 5th, but it's also recommended to have a familiarization session as well, particularly for that eccentric loading that you saw in the video earlier on. It's a most unusual and unnatural movement that you have to undertake. So let's think now about the parameters that we can get from our isokinetic testing. Well, what can we get? Well, we can get maximum moment or maximum torque. So that's normally you take across the 3 to 6 repetitions, and it's the maximal single moment. The average should not be taken either across joint positions or angular velocities. So one of the things that is recommended is you should always work with the max, and you shouldn't take the average. But we've just demonstrated that the average is probably more reliable as long as you are working in that isokinetic phase. If you then take the average across the full range of motion, of course you're going to get a very, very disparate variable. Let's show you that and just explain that in a moment. So if you were to take the average across the full range of motion, you can see that it would calculate all of this torque that you've got in here, and you get a very different average to what you see when the limb is actually working isokinetically. So the average can be used, but only in that isokinetic phase. You can look at the reciprocal. So it's an indication of joint balance. So this is kind of the contribution of, say, the hamstrings to the quads. And we know that that's quite important. Particularly we see this in a lot of athletes where they overdevelop the quads in relation to the hamstrings. But as I've written here, has to be performed using gravity corrected data. I mean, all should be, but this really, really should be when you're looking at flexors and extensors as an example. You could look at the angle of the maximum torque. So this is kind of gives an information about the properties of the muscle. Now this is affected by the velocity of movement occurring, and so you have to be very, very careful of this, because this is where we break our own rule a little bit. So now what we would do is, if we had got this rather than time, we've got this as range of motion on this axis here, then this becomes our maximum torque. We can work it out in relation to our angle of rotation. Notice it's no longer in the isokinetic phase, and that's one of the things we have to recognize. If we're dealing with average torques and we're dealing with kind of peak torques, then definitely take them in this phase here. If you're looking at the angle where the peak force is being produced, the overall peak force, then we have to ignore to a certain degree this isokinetic phase, because we're looking for the angle across the range of motion. These are independent of angle. This is just understanding the isokinetic phase. And then you can look at things like fatigue and endurance. Now under kind of isokinetic conditions, we perhaps define endurance slightly differently. But it might be, you do 30 to 50 repetitions, and then you might look at, well, okay, when did the torque fall to, say, 50% of the peak force or the maximum voluntary contraction, as an example. Or you can calculate a fatigue index score. So if you take, say, your repetitions, your 5 repetitions, what you would do is you would isolate your 3. And what you would do is you take the peak torque, or the highest peak torque, you minus the lowest peak torque, so that would be the rep with the highest, the rep with the lowest. You divide that by the highest peak torque and multiply it by 100, and that gives you what we call a fatigue index variable, or a fatigue index score. And we can see this here in terms of what's going on. Here we've got our position, and this is from different groups of athletes. And here you've got the torques as a percentage of the MVC, and you can see perfectly what we've been referring to. Can you see here that you've got our different angular velocities, and you'll notice at 60 degrees per second here it takes a lot longer to reach the peak torque. So this is where the angle is kind of independent of the angular velocity. Okay, so here's our peak torque here. Notice the peak torque at 180 degrees per second is actually at around about a knee angle of say 50 degrees, and here it's probably a knee angle of about say 60 degrees when we're working at 60 degrees per second. So we can see what happens across the range of motion, and now what we're seeing is in real time the length tension relationship of the muscle. So it becomes a really useful kind of way of expressing what is going on in the muscle. And so you can compare what is happening at different speeds, you can compare how long does it take to reach peak torque, how long do they hold the peak torque for before you get the decline. We can see all of those kind of differences at the different angles. So it becomes really useful, particularly when we start getting into the mechanics of movement and we're perhaps thinking about training responses or even starting to think about rehabilitation programs. So here we've got a data set where what we've got is angular velocity. So we've got our different angular velocities here, 30, 60, 90, 120, 150, 180, 210, 240. And what we've got is we've got them in knee extension, which is the light grey, and then you've got them in knee flexion, which is the dark grey. Okay? And what you can see is if you think in flexion is predominantly from the hamstrings, extension is predominantly from the quadriceps. And what you can see is at higher angular velocities in both flexion and extension, the amount of force being produced is significantly lower than it is at slower angular velocities. And you get this kind of progressive decline. And of course, what you're starting to see here is the force velocity relationship. So if you're not sure of that, go back to previous sessions, perhaps go to the session on muscle physiology within this, and you'll see that there is this kind of relationship which exists. This is under concentric loading, that where we have got a high angular velocity or a high velocity, you'll have low force. Where you've got slow velocity, you'll have a high force. And what would start to happen if we did over more and more of these, you'd actually start to get a very, very nice hyperbolic relationship. So let's see these in action. So this is 60 degrees per second, as we've seen before. So this is kind of aligned to what we see here. So we're going from flexion to extension and back across repeat trials. Now let's see what happens. Again, it's the same range of motion at 240 degrees per second. So you can see an enormous difference in terms of what is going on there. So fundamentally, at 60 degrees per second, if you go back to just basic muscle physiology, we've got the muscle is under tension for longer. Time under tension becomes so fundamentally important. So the net result is there's more time available for an interaction between the actin and the myosin filaments, both in extension and in flexion. Whereas at 240 degrees per second, what happens is there is less time for the muscle to be under tension. The net result is you get less time for an interaction between the actin and the myosin filaments. If we then delve into this a little bit further, here we've got knee angle in degrees. So we're going from 90 degrees to 0, so we're going from flexion to extension. Here we've got our torque in Newton meters, and then what we've got is our angular velocities. So we've got 15 degrees and 180 degrees per second. And what you can see is exactly as we spoke a moment ago, higher angular velocity is associated with a lower force. So its peak force is around about, what's this, about 125 Newton meters. Whereas at 15 degrees per second, its peak force is around about 200 Newton meters. But what you'll also notice is that the time taken to reach the peak force is actually, in this example, it's taking longer to reach the peak force at 180 degrees per second than it is at 15 degrees per second. But you'll also notice that at the slower angular velocity, you get a much, much more rapid rate of decline across the range of motion. We actually sustain this peak angular velocity at 180 degrees per second for slightly longer than we did at 15 degrees per second. You'll also notice the joint angles at which they occur at. So here, if we take let's actually take this one here, which is 60 degree knee angle. So at 60 degree knee angle, we're just about 200 Newton meters. If you take 60 degree knee angle at 180 degrees per second, we are around about 105, let's call that 115 Newton meters. When we come to 45, can you see? We're now down to just about 150. Here, we're probably very similar to where we were before, about 115. So you can see that there are differences in the amount of torque being produced at different angles and at the different angular velocities. So this becomes a much, much more powerful diagnostic tool than you would see working isoinertially or even isometrically. And this is that same data set. So here you've got your angular velocities, and here you've got the joint angles. So what you can see is, let's focus on 60 degrees let's focus on 60 degrees per second for a moment, and you can see at a knee angle of 75 degrees it's 148, 171, 146, 105, 62. So you get this kind of example of length tension. So where you are at in this example here, we're close to maximum flexion. We're not absolutely at max flexion, but we're close to maximum flexion. So you're getting quite a lot of overlap between the actin and myosin filaments. The amount of force being produced is relatively low. We then get to a point where we get optimal interaction between the actin and myosin filament, so then the torque goes up. Now we're going beyond that, and we're starting to get elongation. We're starting to get separation between the actin and myosin filament, and the amount of force we produce starts to decline. What you'll also notice on here is if we then take at any joint angle, so I'm going to take knee angle of 60 degrees, notice now, ignore zero for the moment. What I want you to notice is, if you look at the angular velocities, 15 degrees, 30, 60, 90, 180, you'll notice the amount of torque being produced declines. It's force velocity. High force, low velocity. Low force, high velocity. So this is under concentric loading. Remember that under eccentric loading, the relationship is somewhat different. That under eccentric conditions, which is about braking forces, what we get is high force, high angular velocity. The one that is different here is zero, because zero is isometric. And what you can see is that isometric force, irrespective of the angular velocity we compare it to, at the same knee angle, is always the highest value. And that's because, again, as we learned in the session which is on muscle physiology and force generation, under isometric loading, you're always going to get, or near as damn it, going to get maximal neural recruitment. You're going to recruit almost all the motor units, therefore should be able to induce the greatest amount of force. In this example here, which is data taken from our lab, it's not fundamentally important to understand about these. These are the phases of the menstrual cycle: menses, mid-follicular, mid-luteal, pre-menses. Here we've got data for the extensors and the flexors. But what you can again see is, if you take any of the phases, if you go, let's take menses, you'll see 60 degrees per second, 110, 240, 65. Can you see that as the angular velocity increases, the amount of torque being produced decreases, irrespective of the phase and irrespective of whether you're working in flexion or extension. So it really allows us to separate those out, and you should now be able to work out whether this is being done eccentrically or concentrically, given the relationship we just described. And of course what you should have worked out is that this is under concentric loading: high force, low velocity, low force, high velocity. The data also does show us that there are differences, and this is why isokinetic dynamometry becomes really important to us when we look at the amount of force being produced in, say, this example here, in menses at 120 degrees per second compared to the mid-follicular. Look at the difference in the values, to mid-luteal to pre-menses, and in the flexors, again at 60 and 120, when we compare menses to mid-follicular to mid-luteal to pre-menses. It's beyond the scope of this session, but it might be worth, if you're interested, reading the paper, because it explores how and why we get changes in strength across the phases of the menstrual cycle. And then this final graph here is just to show you everything we've done so far has really been about knee flexion, knee extension. And I wanted to show you this because this just shows us what is done when we're doing a test here, which is internal and external rotation of the shoulder. And they've done this. Here we've got internal and external rotation. And what they've got is they've got it at 60 degrees per second, and they've got it at 240 degrees per second. And what they've done is they've just altered the test positions. They've done it in supine, shoulder at 90 degrees of abduction. They've done it in supine with the shoulder at 45 degrees, and supine with the arm in the scapular plane. And this shows us two things. One, it shows us, as I mentioned before, that you can do dynamometry, isokinetic dynamometry on any joint for any movements. But two, it comes back to that point that we spent quite a bit of time on with this session, which is alignment and participant placement and the method. Change the method, notice where they change from A, B to C, irrespective of whether we're doing internal or external rotation, whether we're working at 60 degrees or 240 degrees per second, notice how it changes the torque value. This in case is peak torque. Notice how it changes it. There are significant differences in all of these domains if we alter the alignment of the participants. So it becomes a very, very important lesson to us in terms of what is going on and perhaps to reflect upon.